Hello and welcome back to Dr. Logic Awkwardly Does Logic in her office. Today I would like to introduce you very briefly to some vocabulary, words that we will use to talk about various formulas in propositional logic. So let me bring up my whiteboard so that we can start jotting some things down. Now, you'll remember from our previous introduction of the language of propositional logic that our well-formed formulas include things like atomic propositions, which are represented by individual lowercase letters in the Roman alphabet, P, Q, R, S, etc. And then for formulas that are potentially formed from atoms or for more complex formulas, we use the Greek letters phi, psi, sometimes also alpha, beta, gamma, and delta, but less frequently. Most of the time we can do everything we want with just phi and psi. So the complex formulas that we can form are things of this form, the little weird wedge followed by phi, phi, upside down V, psi, phi, normal V, psi, and phi, right arrow, psi. So I want to say something about ways in which we can talk about these formulas. All of these are WFFs, WIFs, well-formed formulas, but we can talk about their individual parts. So take this one to start with. This type of formula is called a negation. And it has as a subformula phi without the negation sign in front of it. So phi is a subformula of not phi. That's another way that we can read this sentence. And not phi is the negation of phi. The next one is conjunction. So we call the entire formula, the phi and psi, a conjunction. It has two subformulas, phi and psi. The individual parts, not the part with them combined together. And phi and psi are called conjuncts. So two or more conjuncts make up a conjunction. Next, we have the ordinary V, and this is disjunction. So the entire complex formula is called a disjunction. Here we have, you can probably already guess what the subformulas of this formula are going to be. It's going to be phi and psi again. And in this formula, they are called disjuncts rather than conjuncts. So two or more disjuncts make up a disjunction. And then this last one is a type of formula called an implication. So sometimes we will say that implications are conditional formulas. So conditional and implication are often used interchangeably. Here again, the subformulas of an implication are phi and psi, but unlike with conjuncts and disjuncts, where all of the components that go into a conjunction or disjunction are called conjuncts or disjuncts, in an implication, we have separate names for the two parts. So I will draw this bigger so that you can see. We have phi on the left-hand side of the arrow, psi on the right-hand side. Phi is called the antecedent, and psi is called the consequent. So we will often talk about conjunctions, disjunctions, negations, implications, conditionals, and we will also talk about conjuncts, disjuncts, one formula being the negation of another formula, antecedent, consequent, and every single one of the components that goes into creating a more complex formula will be one of the subformulas of it. So right now I say here that, for instance, in a disjunction phi or psi, both phi and psi are subformulas of the disjunction. But phi and psi themselves might be complex formulas. Maybe phi is of the form alpha and beta. Now, subformulas of a subformula will also be subformulas. So let me write that down so that you've got it you can see what I'm trying to say. So all subformulas of a subformula are subformulas of the complex formula, or the complex way. Now, this is something that's much easier to demonstrate with examples rather than to try to say, yes, the subformula of a subformula of a subformula of a formula is also a subformula of a formula. This might not be the most explicit way of saying what I want to say. So this is something that we'll talk about in the next video when I introduce a notion of parse trees. Parse trees are ways of looking at formulas and breaking them down into their component parts, into their subformulae. So once you've drawn a complete parse tree, you will be able to tell exactly what the subformulas are and which parts are linked together to build the more complex formula at the root of our parse tree. The last piece of notation that I want to mention here is that whatever one of these operators is the last one that you use when you are constructing a complex formula, that will be called the main connective. So the main connective is the last operator used to create a complex formula. So first thing to note is that atoms don't have a main connective. So not every formula has a main connective because atoms don't have any connectives at all, but they're still well-formed formulas. The second thing to note is that learning how to identify the main connective is very important because when I give rules for determining the semantics of these formulas and also rules used in the proof theory, they will always be rules that you apply to the main connective. So it will be very important that you can identify what the main connective of a formula is, because if you try to apply a rule on something that isn't the main connective, you're going to run into problems. So I hope that this gives you a bit of an introduction to some of the verbiage that we use when we talk about formulas, and I hope you join me next time for parse trees. See you then. Cheers.